the sign to the, like if you have a less than or greater than, I think that's what she said, but I couldn't remember what you said specifically.
Okay, that's okay. Yeah, let's finish this. Keep going.
Okay. So yeah, we pick up that constant of t, and we have our constants like all added to the right-hand side. And then we can just use our rules of logarithms, which was if you have a logarithm minus another logarithm, you can take the inside terms. So it would be x over 20 minus x equals to 20t plus c. And we have our initial condition, which I can use now. Since x, when the time is 0, is equal to 2, I can replace the x with 2 here. And that would show that 2 over 20 minus x can simplify to natural log of 1 over 9. And if we go ahead, and I usually like to rewrite this in a form where the natural log can be written as log base e, and we have it of 1/9 equal to c. So I'm going to go ahead and solve for c, and 1/9 is the same as 3 to the negative 2 power. And again, log rules say that we can take out this power here and rewrite it. Since this is natural log, we can take this power and move it to the front, and we're still left with this here in the inside. So then we get -2 natural log of 3. And so this would be the same thing as the constant. So we have -2 natural log of 3 equal to the constant, and I can go ahead and plug that constant back into this equation here. And so I get the natural log of x over 20 minus x equals to 20t minus 2 with the natural log of 3 as the answer. How exciting.
That's why you have different answers, huh?
Yeah.
Yeah, she did get an x equals to da 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 da, and you get an involves x and t. All right.
So I should continue solving for x just so we can get it in terms of x equal to t.
Yeah, that's the ideally, right?
Right. When I did that the first time, I saw that she got like a really big expression at the end. So I thought I was doing something wrong when I, like you can raise this to the power of e, this to the power of e, and then solve for this. I thought I was doing something wrong because it just wasn't adding up for me. So I went back and like did this like half of the question, probably twice.
I see.
So I left it like this instead.
All right, that's okay. Right, that's okay. You did your best. All right, let's see. You're welcome. Thank you. What's next? Katerina. Yaprak. So which question you have? Is it from 5 or from 6?
I actually found online.
On online, it's for section 5, for lecture 5.
Yeah, lecture 5.
Okay, let's do it. Yeah, go ahead. Okay, Zihao is asking resubmit homework. No, you don't have to resubmit homework. Resubmission is only for one student. She's not able to. She did not understand how to submit. So I created it for her. You don't have to resubmit.
Can I begin?
That's okay. You just submitted. That's okay. Yeah, go ahead.
Okay. So my question was asking, so the question is, 2 monkeys are placed on an island. After 5 years, there are 9 monkeys, and the estimated carrying capacity is 25 monkeys. When does the population of monkeys reach 18 monkeys? So this question involves the logistic equation, which is dp over dt equals k times m minus p to the power of p. So
To the power of p or multiply by p? Multiply by p, I think.
Yeah, oh yeah, so I'm sorry. Yeah, it's the multiplication of p. I didn't write it properly, that's why. Sorry, I just confused. So to separate the variables, I rearranged the equation. So left-hand side, right here, again involves partial fractions. So we calculated for that, and here I got, so this was the result, 1 over 25 times 1 over p plus 1 over 25 minus p dp. I also plug it in m equals 25 as well, as I was calculating the fraction. And then the right hand side is just basically integral of k times dt, which is kt plus c1. And then we have this right here, the integral. So this is the constant, 1 over 25. This goes out of integral, and then we left with 1 over 25 times ln, and I also use the log properties here to get this, and this equals to k times t plus c3. I also combine the constants here, and then to get rid of from the 1 over 25, I multiplied by 25 the equation here, and then yeah, we get this thing, and then to get p equals to something, I needed to take the natural log of, I needed to take the natural log, and then to find the c constant, we use the initial value because we were told that there were 2 monkeys initially. So we plug it in, 0 for t, and then 2 for p. And then we find, I'm sorry, did you say something?
No, I was just clear my throat.
Oh, I'm sorry. And then constant turns out to be 2 over 23. And then to find the k, the rate, we use this given value because we were told there were 9 monkeys after 5 years. And then after calculating it, I got k equals, where is it? Right here, 0.0149. And then the question was asking how many years later there will be 80 monkeys. So we use this equation to find it, and then I solved for t, which is 9.09 years.
Okay, I have one question for you.
Yeah, sure.
Right, just this step. How do you know you can just take off the absolute?
For which step? I couldn't see. I'm sorry.
Oh, you don't see my drawing. I circle this. Let's see. Can you see my circle? No.
No.
Okay.
Oh, here. Oh, yeah, I see that. Okay. Well, because the carrying capacity is greater than population.
Good job.
That's what I thought.
Yeah, you're right. That's exactly right. Yeah.
I'm kind of confused with that, like when we need to switch the signs.
It's in the context. You see, in your case, right? In your case,
yeah.
Right. In Katerina and Gregory's case is a little bit different. But in your case, you know the carrying capacity is 25. That's why I mentioned this.
Yeah, so when the carrying capacity is greater than the population, then we can
right.
take
we assume, right? So
usually
we assume this. We assume. So the ideal situation is the carrying capacity is greater than the population. If the population is too big, it's gonna be big disaster. So
Oh,
M
okay.
greater
Thank
than.
you. Thank you for the clarification.
No, you answer right. I didn't clear anything. Let's see who's next. Shu Xian 5.5. Shu Xian, are you talking to us? Oh, I think your echoes somehow. I cannot figure out what you're saying. Oops. Oh, okay. Her work is up. Can you turn off your mic, then turn it back on? Isn't this the same question? 20x minus 5x squared? Oh, okay. You just change the number, I guess. Cannot figure out what you're saying, Shu Xian. Cannot, right? Just hearing your mumbling, but cannot figure out what exactly you're saying. I have no idea what you are saying. Yeah, I don't know. I don't know. Your side has some problem. Just hearing your mumbling, but cannot figure out what exactly you're saying. I can't understand what you're saying. No, it's the same. You use external mic? I cannot figure out what you're saying. I'm sorry. Okay, you try to fix that. If you use external mic, I don't know, you have to change one or something. Let's go with Ryan. Ryan. I can't understand what you're saying, Sushan. Let me go first. Ryan.
Yeah, I'm here. I'll pull it up in a second.
Okay.
So I slightly modified question 6.2, called it 6.4, but it's in a sense the same question. So I have it. A car is traveling at 200 kilometers an hour, and the driver hits the brakes. After 10 seconds, the car is traveling at 195 kilometers an hour. Suppose that the resistance, so in this case, that would be air resistance and from the tires, is proportional to the square of the velocity, so that the time derivative of velocity, which is acceleration, is equal to negative rho v squared. So in this case, rho is what we would typically use k for. It's a rate, basically. And in this case, it is the resistance. And so the question asks to find the velocity of the car and the distance traveled, t seconds, and I wrote after the brakes fail. And then I added another part, which is when will the car be at rest? So basically solve for v equals 0. So the first thing to do is to basically just write the function as given. So acceleration equals negative rho, my rho's look like these, but negative rho v squared. And what we can do is we can we can divide v squared on both sides, and we can leave negative rho on the right side, and then we can multiply dt on both sides. And so we've basically separated the variables into v on one side and rho on the other side. Of course, rho is a constant, so when we integrate with respect to t, we're just going to get a constant times t. And over here we have basically v to the negative 2, and that basically just becomes negative 1 over v plus a constant. And again, negative rho times t plus a constant. We can merge the constants into 1 because they're just numbers. And I negated both sides. And then I just flipped them, because if we have the inverse of v, then we can invert the other side to get v back, and that equals the inverse of the other side. So velocity in terms of time equals 1 over rho t minus c. Now, we have that the car was driving 200 kilometers an hour at time equals 0. So what we can do right now is actually solve for the constant. So we plug in 0 for time, and that's 200 kilometers an hour. The question asked for seconds, so I did a unit conversion, solved for c, and c is negative 0.01. Then we have at 10 seconds, the car is at 195 kilometers an hour. So we can solve for rho. And basically we plug it in for t again. And we go through all the steps. I did a unit conversion. And basically we get rho equals 3 over 65,000. Pretty high number, but basically we can just plug that back in. I did, and I ended up simplifying. So it comes out to this, because it's in the numerator. So I'm sorry, it's in the denominator. So you can pull the new denominator, which would be 65,000, into the numerator. You basically just flip them. And I integrated both sides again because we have velocity, but we're looking for time. I'm sorry, for position. We're looking for position, so I integrate both sides with respect to time. And doing that, we get position plus a constant equals, and then here we have t on the bottom, and we have a constant, and basically another constant. And so it's just the log of the whole denominator multiplied by the numerator. And so that's right here. And it is the absolute value. However, time is always positive. So we can basically get rid of the absolute value. And of course, we have the constant. We can convert the constant into just the 1, get rid of the absolute value, and we have our function for position, except for we're missing C. So
Hold on one second,
Mhm.
Ryan. So when you integrate 65,000 over 3t plus 1170, because the 3t, don't you have to offset with 1/3?
Oh, you are right. I did miss that. But it's just a constant, so it just like that.
Okay, but the 65,000 needs to be divided by 3, right?
Yes, yes. So in that case, it's just like that, and it
Right.
doesn't change the answer by much. It's just a factor of 3. But yeah.
Okay. All right.
So we basically just to solve for C, we have in this case the question doesn't give us the original position, but we can assume that we start at 0, at least for the purposes here. The car starts at position 0 and then moves forward on the, I guess, X, Y, and Z axes, whatever you want to consider. But basically, we assume that it starts at 0. So we can plug in 0 for time, and we can say that 0 equals the function when t is 0. And so our solution for C is going to be this monstrosity, which is approximately equal to this monstrosity, but over 3. And so we have the velocity function, and we have the position function, of course, over 3. And we also want to take that and divide it by 3. And so yeah, those are our final functions. Now, the question also asks, when will the car be at rest? So we can use a little funky math to get that answer. If you look at the velocity, we have essentially 1 over x. We can look at it that way. Not x as in position, but just x as a variable. So we have 1 over x. So the limit of that as it goes to infinity is 0. However, because we have logarithm for position, we know that that will always go to infinity. So the position will always increase, and the velocity will only ever be 0 at infinity. You can't drive forever. So will the car ever be at rest? No, because it's always going to keep moving forward. You should probably just jump out. And because of the high speed, he should wait about 20 minutes before jumping, because otherwise he'll probably hurt himself. And so, yeah, that's sort of a mix of question 2 and also question 3, because question 2 has negative rho v, and question 3 asks us to solve with negative rho v squared. So kind of a mix of both with different numbers. So yeah.
Okay, so function v. All right, the constant is all the I see. Okay, nice.
Thank you.
Nice, thank you. Les 1. Les, are you speaking?
Can you hear me now?
Yeah.
Oh, my bad. So I'm doing question 1 from homework 6. A car's acceleration is proportional to the difference between 120 meter per hour and the car's velocity. It takes the car 10 seconds to accelerate from 0 to 60 meter per hour. How long will it take the car to accelerate to 100 meter per hour? So we know that acceleration is the change of velocity with respect to times. So v is velocity at any time t. We know that the acceleration is proportional to 120 minus v. So we can write a in terms of that. So a equals to k times 120 minus v, where k is a constant. We will rewrite a in terms of dv and dt. So dv over dt equals to k times 120 minus v. So we rearrange that so we can have dv and v on the same side and have dt on the other side. So we're gonna integrate on both sides. Integrate dv over v minus 120 equals to minus integral of k dt. When we integrate 1 over v minus 120 with respect to v, we get ln of absolute value of v minus 120 equals to minus kt plus c. Taking exponential on both sides so we can get rid of the ln. We have absolute value of v minus 120 equals to e exponent minus kt plus c. Absolute value of v minus 120 equals to e exponent minus kt times e exponent c. So now we're gonna replace ec by e exponent c by a. So we're gonna have now absolute value of v minus 120 equals to a minus kt times a. We're gonna call this equation 1. From the problem, we know that at t equals to 0, v is also 0. So we go ahead and replace absolute value of 0 minus 120 equals to e exponent 0 times a. So e exponent 0 is 1, so a is just equals to 120. We're gonna go and substitute that in 1. Absolute value of v minus 120 equals to e exponent minus kt times 120. We're gonna call this 2. We also know that at time equals 10, at t equals 10 seconds, v is 60 meter per hour. So before I replace the time in my second equation, I will have to change the second into hours so it can match my velocity, because my velocity is in meter per hour. So I will change the 10 second into hour. So I just divide by 60 times 60, because 1 minute is 16 seconds, and in 1 hour we have 16 minutes, and 1 minute we have like 60 seconds. So it's 1 over 3060 hours. So when we simplify, we just have 1 over 360 hours. So I go ahead now and replace. So v is 60 and t is 1 over 360. So absolute value of 60 minus 120 equals to 120 e exponent minus k times 1 over 360. I got 60 minus 120 is minus 120. Taking the absolute value, I get 20 equals to 120 e exponent minus k over 360. I divide both sides by 120, and then I got 60 over 120 equals to e exponent minus k over 360. Simplify 60 over 120, that gives me 1 over 2 equals e exponent minus k divided by 360. Cross multiply and move it a little bit around. I got 2 equals to e exponent k over 360. I take ln on both sides. So ln of 2 equals ln of e exponent k over 360. So I know that the ln and the e will cancel out. Ln of e is 1. So it just ln of 2 equals to k over 360. So solving for the constant k, I just cross multiply. So k equals to 360 ln of 2. So I'm going to take my value of k and put it into my second equation in what I call 2. So absolute value of v minus 120 equals 120 e exponent minus 360 ln of 2 times t. So I'm gonna try to find the time, so to know when v gonna be when I know v gonna be equals to 100 meter per hour. So absolute value of 100 minus 120 equals to 120 e exponent minus 360 ln of 2 times t. Minus 20 equals absolute value of minus 20 equals to 120 e exponent minus 360 ln of 2 times t. Take it outside of the absolute value, it's at just 20. I divide both sides by 120. Simplify 20 over 120 gives me 1 over 6 equals to e exponent minus 360 ln of 2 times t. So taking again ln of both sides, so I got ln of 1 over 6 equals to ln of e exponent minus 360 ln of 2t, which is just minus 360 ln of 2 times t. So t equals ln of 1 over 6 divided by minus 360 ln of 2. So I got the time. Remember, I converted my time from second to hour, so my answer is in an hour. So I times back by 3,600 seconds to get back my time in second, and t is equal to 25.05 seconds. So the core, it would take like 25 seconds for the core to accelerate to 100 meters per hour.
All right. Okay. Nice. Okay, Christian, you want to present from questions homework 6. Then David, same thing, right? And Sushan, if you fix your max.
You can hear me?
Christian, yes.
Yeah. Okay. The question I have is a scenario that's more on par with Ryan. It's a mixture of question 2 and 6 for homework 6. Okay.
Yeah.
Sharing screen. Okay. You can see it?
I think it's coming up.
Okay.
Yes, now.
Okay. So I have a hypothetical situation. It's on par with what is expected for you to do for question 2 for homework 6. I felt it was like more interesting to like use resistance as something different other than like the surface you're like braking on. So the question goes as follows. Suppose that a motorboat is moving at 100 feet per second when its motor suddenly quits after hitting a whale on the coast, and that 10 seconds later the boat has slowed to 3 feet per second. So similar to Ryan's, it involves resistance. So assume that the resistance it encounters while ramming into a whale along the coast is proportional to its velocity. How far would the boat travel? And the secondary question is, assume that the resistance is proportional to the square of the velocity. How far does the motorboat travel in the first minute after its motor quits? And that's a little whatever representation there. So I'm going to tackle the first question by having the rate of velocity relative to time is equal to, Ryan used rho, I used k. It's just a variable, whatever, that we chose to use, but it involves the resistance. Is representative of the resistance, so negative k multiplied by the velocity. And so right now we're going to separate our variables, multiply each side by dt over v. That helps us to have 1 over v on the left side and negative k on the right side. Integrate the left respect to v, right respect to t. Our result is ln v is equal to negative kt plus c. And after that, we make them both of base e. In doing so, we'll have v is equal to a being some constant multiplied by e to the power of negative kt. And we're solving question 1. So we have to take into account that when velocity is 0, it's equal to 100 feet per second, and when velocity is 10, it's equal to 3 feet per second. It's because we need to solve for our a and our negative k constants. Well, not negative k, but k constant. In using these conditions given to us, we could come to the conclusion that 100 is equal to a times e to the negative k times 100, which is just a is equal to 100, and then we'll use that v after 10 seconds is equal to 3 feet per second, and then we can make the equation that 3 is equal to 100, because we already found out that a is 100. 100 times e to the power of negative k times 10, and then that will give us ln absolute value 3 over 100 is equal to negative 10k, and then we divide by negative 10, and then we get k is equal to ln absolute value 3 over 100 over negative 10. So that's our k, and this is our a.
Hold on. We don't like to divide by a negative number. Can you simplify this? Can you simplify your k?
Simplify.
Yeah. You can simplify.
I know that ln of 3 over 10 to a negative value.
That's right.
So you could see it and view it as a positive.
So
in actuality.
Right, ln, you don't need the absolute value sign anymore. So ln 3 over 100 over negative 10, you can change it to be ln 100 over 3 divided by 10. Right? So that's how you get rid of this negative sign. Does that make sense?
So
I'm writing the
can you write on it? Or
I'm writing in the chat. So ln 3 over 100 equals to negative ln 100 over 3. You see it in the chat? ln 3 over 100 is a negative.
Oh yeah, I got you.
So
you took out the reciprocal and inside, and then took out the negative. Yeah.
Right, because ln 3 over 100 is ln 3 minus ln 100. Right, you factor out negative sign.
Okay. I'll definitely keep that in mind for next time.
Yeah, because mathematics, whenever we want to simplify, we can simplify, we want to simplify it. Okay, keep going.
Okay. So yeah, let me go back. Okay. So therefore, okay, we have both of our constants. We can bring it all together. This could have been simplified more, as Professor Chen said, so we wouldn't have to worry about the signs, but the math is the same. It would just be easier the way she said it. Therefore, our velocity is equal to this, with all our constants incorporated. And with that in mind, we're going to separate variables with the definition of velocity and solve for x, which represents your distance. So we have our velocity is equal to this, but we don't want this. We want the distance, but this is going to help us as we go on. So dx over dt is equal to our velocity. That's a definition for velocity. And if you multiply on both sides dt, you get that it's just going to be 1 on the left side, and on the right side is just going to be v dt. And we know that our v is equivalent to this right here. But instead of like writing it all out with all our constants in there, I just use the variables that they're equal to. So k and a, well, not a, but just k, because it's very large. Well, it could be bothersome. So I just put k right there. And I integrated on both sides from 0 to x on the left side and 0 to t on the right side, which is going to be a sort of trick so that we can come out with a function x in terms of t. And this function,
hold on.
Yeah.
One question. Why we made the definite integrals? Because so far we have been using infinite integrals and indefinite integrals. We don't need a lower limit, upper limit. Why you put the lower limit, upper limits here?
I'll put that there because I solved the question in a certain manner that yeah, I'll just explain it, and then if you're confused, you could just cut me off, right?
Because I'm just worried you're gonna lose the constant term.
Oh no! I have the constant. So
okay, keep going.
Okay, yeah. So I keep the constant. Okay, so I integrate both sides. The left side I have x is equal to 100. I factor this out right here. Is x is equal to 100. The integral from 0 to t. So for the right side, I'm integrating the velocity on the right side. So that's going to be the distance in position, and it's going to be in terms of it's going to be from 0 to t. So the outcome of integrating this is going to be the difference from after I'm evaluating it. I find my my antiderivative, and then I evaluate it. I will have a difference from 0 to t. So if I choose any t value, it's going to tell me the distance from 0 to that time, so I can find the distance. So with that in mind, and now I have a function that tells me the difference in position from 0 to any t that I plug into it, I found the limit of that function I found the limit of the function as t is approaching infinity, which is representative of this graph right here. So if you are you confused, Professor?
No, not at all. So you actually use your 0 for your constant term. I understand now.
Yeah.
Yeah. Keep going. Go ahead. Very nice. Yeah.
Okay. So I take if I take the limit as t is approaching infinity of the integral that I just found for the velocity function that we came up with, right? Then I'll have that the total distance traveled is 285. But the thing is, 285 feet. But the thing is that it is a tricky situation, because in certain situations, you just can't go by that, because there could be an oscillation of for instance, if we were talking about particles, you can't always say, oh, the total distance is from 0 to whatever. As you go on from 0 to 100, you have to take into account that it may oscillate. But the assumption that we're doing is that it's just going straight forward. It's not going back and forth at all. And so, yeah, that solves for the first one. The first assumption, the first question. The second question is more aligns with homework 6. The third question, yeah, because we have velocity squared. So same thing we did the last time, dv over dt is equal to negative k v squared. Multiply both sides by dt over v squared. And then we transfer it transfer vice versa the variables that we want on their respective sides. We have 1 over v squared on the left side, and then we have we didn't transfer anything on the right side, sorry. But yeah, we did. We transferred dt, my fault. Okay, we got the v squared right there, left, dt to the right. In doing so, we integrate both sides, and then we get negative v to the negative 1 power is equal to negative tk plus c. And multiply by negative 1 on both sides, because we want to get rid of this negative for this v we want to solve for, which is our velocity. Multiply by v right here, multiply by v on the side too, and then we get velocity is equal to 1 over t times kc. So yeah, after that, we are going to do the same thing. We have constants we need to find. We need to find our c and our k. So we're going to use that v at time 0 is equal to 100, and v at time 10 is equal to 3. And okay, so with the first one, we have 100 is equal to negative 100 is equal to 1 over negative c multiplied by negative c on both sides. This is after we plug in 0. We get 1 over negative c, if you notice. So that's how I got 1 over negative c right here. Multiplied by negative c on both sides. Then you got 1 over 100. Divide by 100 on the left side and on the right side. And then keep on going down. And then you multiply by negative 1 because you want to make that c positive. So then you have c is equal to negative 1 over 100, or negative 0.01. Yeah, I don't like decimals, but I don't have space right here, so I just... Huh?
0.01.
Yeah, 0.01. Yeah, I have it right here. So yeah, we got that, and 0.01. I set the velocity function with in respect to velocity at 10 seconds. So it's 10 right here multiplied by k, and then you have the negative of 0.01 as Professor Chen said, and it becomes a positive because in our original function the constant has a negative right next to it, so it becomes a positive. And multiply by 10k plus 0.01 on both sides. Then you have the 10k out of the equation right here on the bottom of the denominator. Then you divide it by 3 on both sides, the left and the right. You have this inside expression equal to 1 over 3, subtract by negative subtract by 0.01 on the left and right. Then you have 10k is equal to 9 over 300. Divide by 10 on both sides, you have your k. If you simplify this, keep change flip, you have k is equal to 91 over 3000. And we have both our constants once more, and we just gotta rinse and repeat. So even though it's a slightly different question, dx over dt is equal to our velocity, and so we have dx dt over dt is equal to the expression we just found, and then we're going to integrate both sides. Okay, so we're going to get in respect to t, so we're going to get x right on the left, and then for the right side it's a little bit more work. We got to do some use substitution, which is cool, and it's annoying. Okay, so you take out the 100, take that out in front of the integral, and then you set your u equal to your denominator, which I did right here, and then I have my du right here, multiply the du over du over the fraction 97 over 30, and take that 97 over 30 outside the expression, and then it's going to be the reciprocal, and you have basically 100 times 30, that's 3000, over 97 as we go down right here. And 1 over u is just ln with the u placed back inside. And then we pick up a constant plus c. What does that c equal to? Let's find out. When you plug in x at times 0, you get 0. So yeah, when you set your x, your t for the your function equal to 0, you get your constant is equal to 0. And then so now that we know our constant is equal to 0, and we want to find out what happens in 60 seconds. Oh my God, I'm taking up so much time. Okay, so you put in 60 seconds, and then you get the answer is 160 feet. So you traveled 160 feet after 1 minute of the motor quitting. That's the answer.
All right. Thank you. Very nice. David, do you want to present?
Yeah, sure. So I made a problem based off of homework 5. Here it is. Okay, so the question is like this: the number of students in an advanced mathematics class is inversely proportional to the cube root of P of t, where P of t is the number of students. On the first day, there are 27 students, and after 2 weeks, there are 35 students, and there are 40 seats total. So how long is it going to take for the classroom to reach capacity? So what we have to do is we have to look at we'll just identify what's what first. So beta is the rate of students enrolling. And so we can set that equal to alpha, or just a constant, over the cube root of p. And then the rate of students dropping out can be delta, and we could set that equal to sigma over cube root of p. P naught, basically p at time 0, is equal to 27. That's how many students we start off with. P at 14 is equal to 35, because 2 weeks is 14 days, and we're using days as a unit here. And then here's the original formula, dp over dt equals beta minus delta, all of that times p, the number of students. And so we can substitute in our beta and delta for alpha over cube root of p minus sigma minus cube root of p, all of that times p. And then we can simplify. So, when you divide, you can factor out the cube root of p, and you divide p by cube root of p. It's basically 1 minus 1/3, which you end up having p to the 2/3 power, equaling dp dt. And then you can separate your variables. So over here, we just multiply the left side, both sides by dt, and then divide both sides by alpha minus sigma. And then we can integrate on both sides. And here I let the two constants equal k, because I didn't want to deal with two constants. I'd rather just deal with one, because it's the difference of two constants. And then as we integrate, here on the left side, we have 3p to the 1/3 plus a constant. On the other side, we have a k of t, because we just tack on a t to the constant, and then plus c2. And I simplify this. I say let c2 minus c1 equals c3. And so that's what we have here underneath. 3p to the 1/3 equals kt plus c3. And then we can further simplify this, because we're trying to just get population by itself as a function, by dividing both sides by 3. And so that's what we have right here in the middle. And then we can cube both sides to get p by itself. And so we're going to need to find the constant c, and we're going to go after the constant c instead of k first, because we have a time at 0, p naught equals 27. And so that's useful, because we won't need to deal with k, because it's going to be canceled out when we plug in the 0 for t. And then after some algebra, we find that c is equal to 3. And then we can plug that into the original equation. And now we can find k, because we have another thing we can plug in. P of 14 equals 35. And so basically we simplify that again, and over here we end up getting k equals this decimal over here on the right bottom hand side. It's some algebra, but it's just subtracting, dividing, and flipping some stuff. And so after this, if we want to find, the original question was to find how long will it take for the classroom to reach capacity. That means when there are 40 students signed up for the class. And we can find out how long it's going to take by just for P of t plugging in 40 and then solving for t. So here we have that on this third to last line. Some algebra, just taking the cube root and dividing by 3, and then flipping the stuff on the left side to the right side, basically multiplying by 3, then dividing by k, 0.0581. And this ends up being 21.6896 days, which is approximately 22 days to reach 40 students for the classroom to be closed off.
Nice. All right, thank you. Thank you. So that left for Suxian. Suxian, is your mic working now?
Hello?
Yeah, you're right. You're fine now.
Okay, so, you hear me, right?
Yeah,
Okay,
sounds
so
good.
I change my device, okay, and not the microphone. So let me upload. Can you see?
Yes.
Okay. Today I present and then picking the question is solve the logical differential equation without using the general formula. And by giving is ds over dt equal 20x minus 5x squared. Is initial value is x times 0 equals 6. So
We read it as x of 0.
oh,
X of 0.
of 0. Okay, thank you. So I keep the left hand side dx dt is same equal. I can change it because 20x I can write like 5 times 4 times x. 5x squared I can times 5x times x. So that's why I take the 5x same factor and then the sum of 4 minus x. That one I can divide both and then the x times 4x. So that's why we can become like a dx over x times 4 minus x equal 5 dt. So I integral like both sides, dx over x4 minus x equal integral 5 dt. And then the integral 5 dt is 5t plus c1. So for the left hand side, I use the partial fraction because it separates the denominating. So a term over x plus b over 4 minus x is I can write and then the make like a same denominator. So when a over x is a times 4 minus x over x times 4 minus x and b x and then the over like x 4 minus x. So x right say we can cancel denominator. So I close them is 1 equal a times 4 minus x plus bx. We can write like a 4a minus 4x plus bx, and then we took like a x like a out like a 4a plus x times b minus a because that equal 1. So and then the 4a like constant, so b minus a suppose equals 0. So when b minus a is 0, so 4a is equal 1. And then we get the a equal 1 over 4, and b same thing, 1 over 4. So we get the left hand side 1 over x times 4 minus x equal 1 over 4 over x plus 1/4 minus x. And then we get like 1/4 put in the front is 1/4 times 1/x plus 1/4 minus x. So you know, in the front I integral like a dx over x times 4 minus x is equal this one because they are same thing. Integral 1/4 times 1/x plus 1/4 minus x dx, and then we integrals and then they're like both. So 1/4 is constant, it didn't change. But I integral like a log ln, no, 1/x, I got like a ln x, and then the when I integral 1/4 minus x is ds, this term I use the u substitute, and u equal 4 minus x, I get like a du is negative dx. So it's integral 1/4 minus x dx, and then I got like a negative nu, plug in the u is negative the log, and then the 4 minus x. So we get plug in over there 1/4 ln x minus ln 4 minus x plus c is equal 5t plus c1. So I have the 1 because when you ln x minus ln 4 minus x, I can write like ln x over 4 minus x, because 1/4 is constant. We just write down equal like a 5t. And then because z1 and z2 is constant, I can make together is and get another constant c3. I can write down like ln because that's 1/4, and then I put both side and times 4. I get ln x over 4 minus x equal 20t plus c4. Okay, we get both have e, so we cancel. So the left hand side is over x over 4 minus x equal e 20t times e power c4. So I put over here, and then the e power c4 equal like a c. I use a c5 and in steps. So that's why this one I get like a c5 times e20t. So we know like initial value is x over 0 is 6. And then I plug the 6 into here, is get 6 minus 4 times 6 equals c5 e20t. And then I got like a c5 is 3. So we plug in the c5 into the function, and x over 4 minus x equal 3e20t. But as we know, because I integral 1/4 minus x dx is negative. So that's why x over 4x minus x is less 0. And then the 4t is greater than 0. So that's why I get like a negative x over 4 minus x is equal 3e power 20t. So we solve like a t, like get x equal negative 3e, like a power 20t times 4 minus x. And then we simplify, and then they remove the 4 minus x to the another side, and then we get x is times 1 minus 3e power 20t equal negative like a 12e power 20t. So I get the final answer like x equal negative 12e 20t over 1 minus 3e 20t. Well, I can simplify. Maybe I didn't do it because, and then I forgot. Maybe I can like time both is 12e 20t over 3e 20t minus 1. That's my final answer.
Yeah. Very nice. Very nice. E to the power 20t. Okay.
Yeah, thank you.
All right. So anyone else like to present? It's 9:35. Okay, let me quickly go over velocities, which we had enough presentations. So I think, okay, I was checking this one. I see the presentation grades. You see, some of us has reached halfway to be done, but some of us haven't even started yet. So not enough presentations. Yes, that's why you can make up your own question. So we have, I forgot whom. Search the online, find a question. You know, you can make up your own questions. Why this says one new chat message, but I just don't see it. Okay, all right, so that's just okay. All right, so yeah, that's my only concern. All right, so just if not enough questions, make up your own questions and make it interesting. Right, you can do that like a Christian did, or right, like who's another one did, or you just pick up one question from the homework, change the numbers. Let's see. Okay, so we're supposed to talk about velocities, right, for today, which is 6, which thanks to those students who, you know, went before us, velocity and acceleration models. All right, we know the relationship, right, between, we have position function or displacement function. Usually we use x of t to represent. Then we have velocity function, which is x prime, which is v of t. Then we have acceleration function, so a of t, which is a of t, which is v prime of t, the derivative of velocity, which is the second derivative of the displacement function. And we have air resistance, or sometimes the surface resistance. We do have resistance. So this is saying, okay, let's start from the beginning. We only have 22 minutes. But, okay, maybe I'm not able to finish. If I'm not, I don't think I am able to finish, but let's just start this. So mass near the Earth is under the influence of gravity, of course, which accelerates the mass towards the Earth at 9.8, this is miles per second squared. No, meters, which is 32 feet per second squared. Assuming we ignore the air resistance. So the force on mass m experiences a force of gravity given by this. Now let's consider the resistance. So we have this equation, which k itself is a positive number. If the object is falling, then v is negative, k is positive. So we have this. Negative times negative to be positive. Negative times positive is positive. Newton's second law of motion, right? Force equals mass times dv over dt, the velocity. And it can be described in this way, negative kv minus mg. right? If we rewrite this equation, we get a dv dt equals to negative kv divided by m minus g. This k is not always, just in this case, k is positive, all right? In this case, in this equation, k is positive. That's why negative k is, because it's resistance. Negative k is negative, but k itself is positive. David?
Aren't the forces going in opposite directions though? So how are they both negative?
Which one both negative?
F equals negative kV minus mg. Isn't friction going up and gravity pulling down?
Air friction, air resistance. Air resistance going upwards?
Yeah, if something's falling, right, then...
Oh, I see your point. Yes, we're talking about the falling case. Yes, in this case, yes. So what's your question? Do you have a question?
Oh, I was just going to say, shouldn't it be positive kV minus mg?
No, k itself is positive, but negative k. This represents the air resistance.
Okay.
Yeah. It's because V is negative. K itself is positive, but V is negative. So negative, V is positive. Okay. So we can rewrite this equation in this case, dv dt equals to this, negative k v divided by m minus c. Or as Ryan used the notation, so this phi looks like a p, but it's reading as a phi. Negative rho, not phi, rho. Phi is another one. So dv dt equals to negative rho v. So rho represents k divided by m, because k and m are two variables, right? Written with two variables. So we just use another we call dummy variable to represent this ratio of two variables. So we're working with this, right? So rho itself is positive, right? We're saying k is positive, mass is positive, mass will never be measured negatively. So it's called drag coefficient. If you want to remember this, that's fine. I never remembered it. Drag coefficient. Let's see an example. So we want to solve this separable equation, dv over dt equals this. So we just separate v and t. So when we do that, what do we get? We get the dv over this equals to dt. Integrate both sides. Well, the right-hand side is easy. The left-hand side needs a little bit of work. Right? Rho is a constant. So I have this. So we only on the left-hand side, what's our variable? Our variable is v. On the right-hand side, our variable is t. So we have this. We can factor out this negative sign, right? And the coefficient before v is rho. So offset with 1 over rho. The absolute value of this, right? If you factor out this negative sign, we don't have to deal with this negative here. In any case, as Ryan just did with, because we add C1, add C2 on both sides, we don't really have to do that. Just add C on one side. Okay, instead of adding C1 or adding C2 on both sides, just add C on one side. Because it just represents a constant. Simplify, multiply by rho on both sides. Right. Then this is saying because negative of this, because v is positive, this is positive, so negative, and then this negative, this all negative is less than 0. So absolute value has to be this. So then the above one simplified to be this. We rewrite it because some of you like to see, okay, I take E, I raise both sides by to be the exponent of E. That's fine too, but that's an easy way. Our n means the base of this log is E. So we just rewrite this equation as E raised by this exponent equals to the value, right? So E raised by the exponent on the right-hand side equals to the value. We rewrite this equation, all right? We don't want to raise both sides by the power to be the power of E. We just rewrite this equation. We rewrite the log equation into exponential equation. Then we simplify, we try to solve for V. In the end, we get a V has such presentation. Right. Right. If V has the initial condition, then we can solve for that. Substitute the variable to be 0, t to be 0. Then we get the initial velocity to be this. So substitute in. So we get a velocity function. As Christian showed, right, we want to take, sometimes we need to take a limit, let the time t run to infinity. It's just an idea. Just basically saying, you know, let time keeps running, keeps going. And then this is to be called terminal velocity. So in the end, this thing, a falling object has a terminal speed of such. I think this is reading as tau. It's another Greek letter. So equal to such. Remember, rho is k over m. So we can rewrite it as this, m over k for 1 over rho. And rewrite v of t back into rho case. So we get this back into rho and this terminal speed. Terminal velocity, not terminal speed. Terminal speed is the absolute value of it. Absolute value, because the velocity can be negative, can be positive. Speed is absolute value of the velocity, cannot be negative. They say if let y of t to be the distance of a falling object above the ground, then we have dy dt, right, equals to the velocity, equals to such representation. So integrating this equation, so we get a function of y in terms of t, right? Just integrate this side, so we get this. So this just changed the, just talking about two scenarios, okay? Just use the different variables to represent. One is talking about displacement, one is talking about falling object, but the representation, you know, are very similar. Let's see an example. A car is traveling at 88 feet per second, so 60 miles per hour. After the engine shuts off, after 20 seconds, the car is going 11 feet per second. Assume that the resistance it encountered while coasting was proportional to the velocity. How far will the car coast before it stops? Right, proportional, so we use this, dv dt equals negative rho v, and the separate variables, integrate both sides, pulling the negative sign before the integration, integrate, get this, then simplify the equation, rewrite the log equation as exponential equation, right? Then that means the velocity function is such. Use the initial condition, solve for the constant, put the constant back into the velocity function, so get this. Use the second given condition to get a rho. Solve the equation, so get a rho. It's about 0.104. Put it back in to the velocity function. Right. Integrate both sides. Put an initial condition. Of course, displacement at time 0 is 0. Solve for C. Put it back into the displacement function, so we get a displacement function. Again, thinking about the time keeps running, take a limit that t runs to infinity. So that's the it will reach, right? As time running, it will reach such distance. Okay, and anyone has any questions? I'm not going to keep further. So we're going to talk about the rest of it next class. Next class, we'll finish these slides and we'll keep going with so 7. Let's see what's 7. Oh, we're going to second order. Okay, second order, but still linear differential equations. So anyone has any questions for today's velocity and acceleration? So this model we're not strange. It's not strange to us at all, right? We've been talking about, and also the other one. Just this name. This is just a name for it. If you want to remember, that's fine. Yeah, actually nothing's new, right? Oh, next time, right? Next time we will talk about the proportional to velocity square. Okay, anyone has any question? Right, so far we are very familiar with this. Let's see, I just want to ask something about the logistic differential equation. Can you please go over when to take value or when to take a negative value or positive value from the absolute value? Logistic equation. It's in 5, isn't it? Okay, let's go find the logistic. All right, so this is our logistic. I think it's David, right? David tapped in this M, P. So we have this M and P. Let's just go back to understand what is M, what is P. Okay, you see, when we talk about birth rate, death rate, right? Let's start from the very beginning, actually. Because the logistic equation comes from there, or here. With beta of t, delta of t. Beta of t represents the death rate. Delta of t represents, no, beta of t represents birth rate. Delta of t, death, d, right? Death rate. Of course, So we have beta rate. So in this case, beta rate minus death rate. Right, let's argue about this. If birth rate, if birth rate is lower than death rate, this will be a negative number. If birth rate is bigger than death rate, so this will be positive number. So that's the beginning of it. Now let's come to our logistic. Right, so this is a decreasing model, or sometimes maybe we'll have an increasing model. Okay, so equivalently, we come from this. We use m minus p times p to represent. So m, in that case, we don't really have to care about that. So this becomes our model, and we call this logistic equation. Let's see, depends on the example. Let's see this example. So we want to solve this logistic. Oh, see, this one says m greater than p. So this is population growth. So it depends on the question itself. Okay, so each question depends on the context. This is the value of x of 0 represents what? M or P? Writing x of 0. Where is x of 0? Which one you're talking about? Which one? It depends on each question. You have to point out each question. Which question you're talking about. So this depends. So this one is positive or negative depends on the context of a particular question.
But isn't it like the general form of any logistic equation?
Usually, normally, m greater than p. Normally.
So let's say, for example, let's say the number 1 in work 5, when we have x, dx over dt equals x times 5 minus x. So which one will be m in this one and which one will be p in this example?
Hold on 1 second. Which one? Number
yes,
1?
the first one, yes.
5x minus x squared. Okay, so solve logistic differential equation without using the general formula. X of 0 equals to 3. Well, I would just take a 5 minus x is positive. Because this is just pure mathematics, right? If you want to argue with me, I want to take a 5 minus x less than 0. Fine. You just go that way. Because this has no context. This is not a live application. This is just pure mathematics.
So we can do like either one.
This is saying use general formula, right? General formula. The general formula assume m greater than p. Let me check. Logistic equation. Because that's an assumption in there. Usually, because especially when we talk about population growth and the carrying capacity, you know, we assume m greater than p. Yeah, I would guess we assume, so general formula, it's just m greater than p.
So what happened when m is greater than p? Do
Hold
we
on a
take
second.
like the positive one, or do we take the one with the minus?
So, and she's ready. I'm starting presenting next week. Oh, okay. Yes, sure. Sure, Anchi, try your best. Okay. Yeah. Okay, sorry. Liz, what were you saying?
Yes, I was saying, since it's like m, you said it's greater than p, we assume that m is greater than p, right?
Right. That means 5. 5 is m.
Mm-hmm.
X is, that means 5. That means x is less than 5. I guess that's just general.
Okay, so 5 will be the m and 3 would be the p, or x will be the p.
That's right.
Okay, thank you.
You're welcome. Gregory?
Hi, Professor. Can you hear me?
Yes.
Okay, great. So I'm on my way home now, but I really had the question. I think it's the one that Liz just asked, but I'm asking in regards to question 2, since I wasn't available to hear it. Could you possibly repeat? So I was doing the question over again at the part where I messed up on the absolute values. Is because I forgot the integral of 1 over x is a natural log, but absolute value of x, you know? It's like so trivial to me that I forgot to put the absolute value sign. But then when I went back and did it, I got absolute value of x over, I think it was x minus 20. Can you elaborate that again for me, please? I would love to know why.
Okay. So from the very beginning, the equation comes from the birth rate, death rate, then population growth, then, okay, we have this logistic equation. We have this logistic equation.
Right.
We do.
I'm seeing it.
Yeah, in reality, let's go back to the birth rate and death rate.
Okay.
Right. So we use this one, not this one. Let's go back to this one. Because it comes because the logistic equation usually is for population. We have this birth rate, we have this death rate. Can you see it?
Yes, I can see it, but I thought we weren't supposed to reference that equation.
Oh yes, logistic equation usually works for populations. Okay, so this depends on situations. Let's see, we know, you know, a couple countries, the population is dwindling down, which means the death rate is higher than the birth rate. Like I heard French, Japan, even China is facing this huge problem. So this one, in that case, this one is negative. However, in some other countries, like America, Latino countries, the population increasing. So this one, that means birth rate is higher than death rate. So this one is positive number. So it really, you know, if we apply to life situations, for pure mathematics, we don't care. We just do the calculation. But for life situations, it really depends on each question. But just in general, what do? We come up with these logistic equations, logistic differential equations. Most cases, if nothing is stated in the question itself, we just assume m greater than p.
Okay. So when we get to that part that I was confused about, could you possibly like show me the work so that I can finish the equation since I couldn't like finish solving it because I got confused towards the end. And I think a few other people, they did the question, but can I see how you solved it?
Solve which one?
I think it was homework number 5, question number 2.
Not for tonight. Maybe next class. It's already
Okay.
10.
Sure. What time in the class next time could you show me?
Oh, first I would encourage you to talk to your friends, talk to Ryan, because you know.
Yeah, I did. While I was like away, they all showed me how they did it, but I got a bit confused, and like just seeing someone do like the work, like finished work,
You have
like
this.
you could follow it, but I would rather like you show me how to do it like step by step.
I know for today I'm already behind my schedule. I'm behind my schedule.
Okay, no problem. Sorry, it's just very windy outside.
Oh, I see. Yeah, we have
So
time, of course.
okay, no problem. Instead of like doing the whole equation, like the part that I got stuck was after like solving for the constant. Could you like just show that instead?
Well, you get so many volunteers, they can help you. Katerina said you can give her, you can have her, and Yaprak said you can add her. You have many friends want to help you, okay?
Okay, no problem. Thanks.
You're welcome.
Professor, I have a question. For
Yes.
the second question that I did, was my answer correct in order to help Greg?
I think so. I think your answer is perfect.
Okay.
Yeah.
Thanks.
Yeah. I think Gregory, because in principle both of you have done the same thing, but Gregory just went a long way to solve things. Then he got confused. That's why his answer a little bit off.
I got confused towards the end. Like I did the problem like similar to how Katerina did her problem, but then I was getting like really long like answers at the end, like e to the whatever over e to the whatever, and so I did it over again and left it there.
Gregory, let's do this. So this weekend you try to work out again one more time. All right, one more time, especially for your partial fraction decomposition. Try to leave it positive. Try to leave at least the first term to be positive. And make your work much simpler. All right. If you still have a problem, next class after I finish with everyone, you and me we can talk. Okay.
Okay, no problem. Thank you, Professor.
I just don't want to take a class time anymore. All right.
Can I ask one more?
Yes. Yes, Suxian.
Yes. So for number 2, yeah. Is it me? Can you hear me?
Yeah, number 2. Yeah,
for number 2, I saw that Greg got for my answer, I had A and B values that were equal, but for Greg, his value for B was negative. Would it be correct or not correct?
But his answer was opposite. I didn't really have time to examine it, but I doubt, because I think every problem comes from, he used a negative sign. He has a negative sign that he got confused.
Right. Okay. Thanks.
You're welcome.
Okay, I'll be sure to watch out for the negative signs when I do it again.
Okay, all right. Suxian,
Oh, yes, Professor, I'm so appreciate you allow me to resubmit the homework one, but the problem when I try to resubmit it, but I can't because no icon, and then I can click and for the homework one to resubmit.
Oh, some other people resubmitted, so you
I have no idea because I submit already, but when I combine and then all the photo into like PhD, like a one file, so I try to resubmit it, but I cannot find a way to resubmit because I submit already. Maybe he never submitted, so that's why I don't know.
Right, I didn't receive yours.
No, I can't because I submit already, but only question 1.
No,
So,
But you can resubmit. I created a resubmit button for you.
But I didn't see them in my Blackboard. That's a problem.
So even Yu Zihao, he got confused. He resubmitted his, but this is created for you to resubmit.
Let me see. So I am doing another way. Let me see.
Oh, sure. The rest of you are free. Like, I want to be free too. I'm tired too. I've taught 3 classes today. Okay, Shu Xian, you have to try, okay?
Let me try if I can, because I emailed to you already, but
no, I don't accept that. It has to be in the system.
No, so that's why I look, and then I open it now, so I can share with you, but I have no icon to resubmit it.
Oh, it means probably due. Let me see. Probably the time is due.
No. There's no icon, so resubmit. Yeah, review submission history homework 1. Only that, so it's nothing. I don't know. So how can I click anywhere, so nothing resubmit. So I complete that because I did like twice, and the first homework I did the draft first, and then I wrote down very neat and nice, and then I just read very clear. So that's why I don't want and just submit one.
No, the due date is up to 15th. You still have time. You still have 1 more day to resubmit.
But the problem, even though now I don't know how can I submit because the system not allow me to do it. So the problem like this, I don't know.
Resubmit? Because you never resubmit.
Maybe she
I submit already, but I don't know.
Like maybe she already accidentally submitted it, so she can't resubmit it again.
Yeah, there's no icon for resubmit it because I did already. I think somebody needs to remove my submission, and then I can able to resubmit it. So I don't know. That's no icon. I can do it.
Yeah, I saw that the submission opened for me too, but I didn't do it because I didn't want to resubmit it.
That's a big problem. I don't know.
So I think everyone got the resubmission.
Yeah, I got it too.
I don't know why you cannot resubmit, because I see 2 students resubmit. You see Zhihao, he submitted and he got confused. He resubmit. I don't know why you cannot resubmit. Can you show me? Can you show me your screen?
Okay, hold on. Yeah, I will.
The rest of it you are free. Okay, you don't have to be here.
Wait, I can go now?
Yeah, you can go. Sorry.
Yeah, I was getting kind of tired. All right.
Yeah.
Okay. I can leave the session?
Yeah, you can leave the session, of course. Yeah, the rest of you can leave the session.
That's great. Yeah,
Professor, can you see my screen? I show it?
Okay.
Yeah. Okay.
I don't need to see your homework. I want to see your screen about the resubmission.
No, just like screen. So, and then it just show up like this. Review submission history homework 1, nothing else. So.
Shu Xian, you have to get someone to help you. I don't know. You have to go to campus, go on to campus to talk to a technician. Oh, okay, now it's better. Hey, can you go back? Can you go back to the screen?
What time does this class end?
Yeah.
It's 10. It's 10
oh, wow.
Professor here.
Don't move. Don't move. Can you make it bigger?
Here. Oh.
Can you make it bigger so I can see?
It's bigger. It's bigger now.
Hand side.
Which side? Left side or right side?
Right hand side. The right hand side.
Okay, let me see. Here is better.
But I still cannot see it. What's written here? I see. Oh, hold on. I see you have uploaded 1, 2, 3. Is it?
No, it's a homework 1, 2, 3. So that's your PDF, your assignment files. It's not. I didn't upload for homework 1, 2, 3. So
Okay.
I only
Okay.
submission for math 1 and 1 JPEG. So no icon. I click all of them. So even though the playing upload, this is and then the third documentation. So no icon. So let me come back to homework 2. Let me see. Look, when I click to the homework 2, look, there are upload file something. I can do it. Well,
go back. Can you go back?
Oh, here. Yeah, go back.
Go to the very bottom. No. Go back to the homework. Homework 1,
Yeah.
homework 2, homework 3.
Okay.
Yeah.
Here.
Go to the bottom. Go to the bottom.
Go to the bottom? Okay. Oh.
Do you see the very bottom one? Resubmit homework 1.
Ah, thank you, Professor. I'm so sorry. I only
Okay.
at the.
All right.
Thank
All right.
you.
Okay.
I'm so
You're
sorry
welcome.
today. So thank you.
That's okay.
Appreciate. I will do now. Okay. Thank you.
Okay. You're welcome.
Good night. Good night. Appreciate.
Good night. Okay. You're welcome.
Professor, sorry to bug you. I think
That's okay.
you did. I think that second half of my message got cut off. So my final for this class is the same as my final for advanced calc. The exact same.
Really?
Yeah. So I sent you an email with my other professor CC. So I spoke to Professor who's the advisor. He told me that I can take either advanced calc at an earlier time or this class at an earlier time, just so I can write the 2 exams on the same day.
Wow, how do they do that?
Yeah, so
okay,
just check your email. I laid it out. So either
so which one you want to take first?
I would probably
earlier.
Sorry?
Which one you want to take earlier?
I probably want to do advanced calc earlier.
So that has nothing to do with this course then. This course you just take in regular time, right?
Because this course is on campus in Brooklyn College, right?
Well, a final will be on campus.
Yeah. I'm just wondering if you need to proctor it. Because if you need to proctor it, then I can take this course at the right time.
Yeah, I'm going to proctor it.
Okay.
Yeah. Okay, so then you really have to talk to your advanced calc professor. So he or she can set up another time for you.
Okay. So
yeah, I think Brooklyn, yeah.
Because okay. I'll ask if it's easier for him to reschedule, and then I'll get back to you.
Okay. All right.
Okay.
So the Brooklyn College should have what do you call it? Like a testing center. Testing center.
I asked the assistant dean, and he told me to speak to the professors itself. And when I went on to visit the Brooklyn College website, they said it's impossible that this happens. I'm like, well, it happened. So
yeah, it should not be happening.
No, but whatever, it's fine. I'll figure it out. Thank you.
Thank you. Have a good night.
Have a good night. Bye.
Bye.